Okay, let's unpack this. We are diving deep today into the world of quantum software, specifically a high-level programming language called Qmod. You see, quantum computing hardware is evolving at an incredible pace, but there's this persistent bottleneck. Programming these machines effectively is still a major challenge. A lot of the tools developers use right now force them to work at a very low level, thinking about individual gates applied to specific qubits. This makes it really difficult to express what an algorithm is actually intended to do, reuse code efficiently, and adapt it easily to different quantum hardware platforms, which all have their own unique characteristics. Our source material for this deep dive is a technical paper by researchers from Classiq Technologies, where they introduce Qmod. Our mission today: to explore how Qmod attempts to solve this bottleneck by providing a higher level of abstraction. We're going to focus especially on how it handles complex arithmetic operations, which are surprisingly fundamental in quantum computing, and why that's such a big deal for building actual useful quantum applications. Think of this as your shortcut to really grasping the core ideas presented in this paper.
That's a perfect setup. The paper really hammers on that point. Many current frameworks rely on describing quantum circuits at this gate level. You're essentially providing a sequence of fundamental operations. Apply a Hadamard gate here, a CNOT gate there, and they clearly lay out why that's such a struggle for developers. It's hard to cap the high-level intent, when you're down in the weeds of gate implementation. It's tough to write algorithms generally without hard-coding specific parameters or qubit assignments.
Right, sort of locking it in too early.
Exactly. Breaking things down into reusable building blocks is a pain. And then trying to make that gate-level code efficient in terms of limited hardware resources, qubits, gate count, coherence time is incredibly difficult. Plus, adapting it for different hardware platforms, each with potentially different native gate sets or connectivity limitations, adds huge complexity.
Yeah, the paper uses a great analogy comparing this situation to the very early days of classical computing. Before we had high-level languages like C, Java, or Python, programmers were working in assembly language or even directly with machine code. It was, incredibly complex, bringing familiar concepts from classical programming, things like functions, variables, data types, mathematical expressions, and control flow statements into the quantum domain is exactly what's needed to make quantum software development more accessible and productive.
Absolutely. But unlike classical computing, we also have to contend with the unique rules of quantum mechanics. Most quantum operations need to be reversible, with measurement being the big exception. And you absolutely cannot copy an arbitrary quantum state thanks to the no-cloning rule.
That's a fundamental difference.
It is. Another big hurdle is managing temporary storage, what we often call auxiliary qubits. In classical computing, you just allocate memory, use it, and the garbage collector cleans it up, usually. In quantum computing, if you use auxiliary qubits during a calculation, you often need to explicitly uncompute them, essentially running the calculation backwards to return them to their initial zero state.
So they can be reused.
Right, reuse or just return cleanly. And this uncomputation can be computationally expensive. And because quantum resources like qubits and gate depth are still so limited, the compiler's job is fundamentally different. It needs micro-level control for things like compactly representing numbers across minimum qubits. And it has to be smart enough to tailor the gate implementation of an operation based on the specific context, like the range of values a quantum number variable might take.
Okay, so that sets the stage for Qmod. It's presented as the solution that tries to let the algorithm designer focus on what the algorithmic intent
That's the logic.
and leave how the low-level circuit implementation and resource management to automation. The paper mentions Qmod has two ways to write code: its own dedicated syntax and an embedded version in Python. They focus on the Python embedding, which is neat because it lets you use Python's power for things that happen before the quantum code is compiled, like setting parameters based on classical data. You write Python code that builds a Qmod description, and that description is what the specialized Qmod compiler then turns into a quantum circuit.
Right. At its core, Qmod introduces concepts familiar from classical programming, but, adapted for the quantum realm. You have quantum objects or variables. Think of them as references to quantum storage, your qubits. You have to explicitly initialize them. And because of the no-cloning rule, assignment isn't a simple copy. Qmod implements a form of assignment by value that ensures single ownership of quantum data within a scope, handling the necessary quantum mechanics behind the scenes. So you don't have to worry about entanglement side effects from unintentional copies.
That sounds important. Avoids weird bugs.
Definitely. And then you have quantum functions, which are the fundamental building blocks for encapsulation and reuse, just like subroutines. They can take quantum variables, classical variables, or even other functions as inputs.
Qmod also brings the concept of types to quantum data. You have scalar types like qubit for a single qubit,
0 or 1 in the computational basis.
and qnum for representing numbers, integers, or fixed-point real numbers using multiple qubits. Then there are composite types like Quarray for collections of quantum values, and QStruct, which is like a classical Python class, or CStruct for grouping related quantum variables together.
Yeah, a way to bundle things logically.
For QNum variables, the type includes important attributes like the total number of qubits used, how many of those are fractional digits for fixed point, and whether the number is signed. What's cool is you can either specify these details yourself, or Qmod can automatically infer them. We'll definitely need to dig into that inference because it sounds like a huge developer win.
Oh, it is. It's a major feature.
If you look at figure 2 in the paper, you see an example of a quantum struct called MyStruct. It has a Quarray of numbers and a single QNum field. You access them just like in Python using dot notation like s.data or ssum. The example also shows the repeat statement, which is Qmod's way of handling loops over quantum data. It uses a Python lambda function for the loop body. And the paper notes that using repeat with a quantum expression count is generally preferred over a classical Python for loop if the count isn't known beforehand, as it can be compiled more efficiently.
Right. Better integration with the quantum compilation. The paper also explains how Qmod tackles that critical challenge of resource management and uncomputation we touched on earlier. It introduces the within apply statement, specifically designed to express the common quantum computation pattern U-dagger VU.
The conjugation pattern.
Exactly. Where you apply an operation U, then another operation V, and then uncompute U by applying its inverse, UI. This is fundamental in many algorithms, especially those using n-cell qubits. The structure of within apply is key. Code in the within block prepares a quantum state, often involving temporary or auxiliary qubits. Code in the apply block uses that state. After the apply block finishes, Qmod automatically takes care of uncomputing the operations from the within block. If any quantum objects were initialized inside the within block and weren't modified by the apply block, they are automatically returned to their initial 0 state, and those qubits are released. This offloads complex uncomputation circuit synthesis from the programmer. It's a big help.
So it's essentially a built-in cleanup mechanism for temporary quantum work, like automatic garbage collection, but for quantum states.
Exactly. It enforces that necessary quantum hygiene. Figure 3 gives a good illustration in a flip phase function. It allocates an auxiliary qubit O inside the within block. The apply block uses this qubit T to control a phase flip. When an within apply finishes, Qmod automatically uncomputes the allocation of O, returning it to 0 and releasing its qubit. This figure also shows passing a function as a parameter using qcallable and defining a lambda function in line, which is pretty standard in Python embeddings.
Okay, now here's where it gets really interesting, and it's a major focus of the paper. Qmod's native support for arithmetic expressions. When we think about quantum algorithms, many of them involve calculations. Arithmetic isn't just a minor feature, it's fundamental. It's used directly in algorithms like phase estimation, it's used to approximate more complex functions, and it's used to embed classical logic like constraint checks or cost functions into a quantum circuit. Section 3 of the paper dives deep into this.
That's right. Qmod lets you write expressions combining quantum variables, classical variables, and literal constants using familiar operators like ABABA, comparison operators like A, and even Boolean logic operators like A and A.
Just like classical programming.
Pretty much. The difference is, if the quantum variables involved are in a superposition of values, the result of the expression can also be in a superposition. And these expressions aren't just for show. They can be used in digital assignments as the conditions for quantum control statements, think quantum if statements, or for more advanced arithmetic evaluations into different quantum encodings.
Let's start with digital arithmetic, described in Section 3A. The basic idea is to evaluate the expression and store the result in the computational basis, meaning you'd measure the result and get a definite binary number.
Correct. That's the most straightforward way.
You can assign the result to a new uninitialized variable that's out-of-place assignment using in the Python embedding, or modify an existing variable using in-place assignments like in-place XOR or in-place add. But you highlighted something really powerful here: automatic numeric type inference. How does Qmod figure out the right number of qubits and precision just from the expression? This sounds almost magical.
Well, it's not magic, but it's clever compilation. This is where a lot of the power lies, and yeah, a huge headache is removed for the programmer. Qmod statically analyzes the expression at compile time. It looks at the types and possible ranges of the input variables and constants. Then, using techniques like interval arithmetic, it calculates the absolute minimum and maximum possible values the expression could ever evaluate to across all possible inputs. Based on that calculated range, Qmod automatically determines the smallest possible number of qubits, the signedness, and the number of fractional digits required for the target QNO variable to precisely represent that entire range of values.
Wow, so the programmer doesn't have to sit there calculating bit sizes and decimal places based on potential worst-case scenarios. That sounds like a massive time saver and error reducer.
Exactly. It dramatically impacts the efficiency of the generated circuit by using the minimum necessary qubits, and it removes a significant burden and source of error for the developer. Figure 4 in the paper gives a perfect example. You have the expression 0.25 AB plus 1.5. Variable A is a 2-qubit unsigned integer, so it can represent 0, 1, 2, or 3. Variable B is a 2-qubit signed number with one fractional digit, so it can represent negative 1.0, 0.5, 0.0.5. Qmod takes these inputs and the constants 0.25 and 1.5. It calculates the minimum possible value of the expression. Let's see, that comes out to 0.75. And the maximum is 1.875.
Okay, so it knows the exact range.
Right. Then it determines that a 4-qubit unsigned number with 3 fractional digits is the optimal way to represent any value within that 0.75, 1.875 range using the minimum number of qubits. That level of detailed qubit management and representation is usually entirely manual for the programmer.
Got it. So it doesn't just calculate the range, it figures out the best qubit representation for that range, minimizing resources.
Exactly. And for those in-place assignments like in-place XOR, the compiler also handles details like sign extension or truncation if the result doesn't perfectly fit the existing variable's format. And it automatically ensures any discarded qubits are uncomputed and released, maintaining that quantum hygiene. Figure 5 shows a clever use of in-place XOR. It's used within a phase oracle, a common technique in quantum search algorithms, to flip the phase of a state if a certain condition is met. The condition is a Boolean expression, R0, R1, which checks if the first 3 elements of a quantum array are sorted. The result of this Boolean expression is computed digitally and then XORed onto a result qubit.
Which effectively flips the phase if the condition is true.
Precisely. If the result qubit was initially 0 and the expression is true, it becomes 1 and vice versa, which creates the phase flip. Notice the use of the bitwise operator. You can't use classical Python in here because you need the quantum expression to be fully evaluated, even if the first part is false. No short-circuiting in superposition.
The paper also mentions that dealing with precision, especially with classical floating point numbers mixed into quantum expressions, can be tricky. High precision needs lots of qubits.
It can, absolutely. Full precision might require an impractical number of qubits. Qmod allows setting a maximum machine precision. If an expression would require more qubits than that maximum to represent precisely, Qmod automatically truncates the least significant bits. Crucially, it ensures the qubits for those truncated bits are correctly uncomputed. The compiler then optimizes the gate synthesis for the expression and manages any necessary auxiliary qubits.
Okay, so digital arithmetic is powerful and gets automatic qubit management. But this is quantum computing. It does weird and wonderful things beyond just calculating numbers you'd measure in zeros and ones. Does Qmod let you work with, say, the phase or amplitude of a quantum state directly using these expressions?
Absolutely, and this is where Qmod gets even more unique compared to many lower-level frameworks. It natively supports non-digital arithmetic, meaning evaluating expressions not just into the computational basis, but into the phase or amplitude.
Okay, tell me about that.
First, arithmetic in phase, section 3b. Data can be encoded in the phase of the computational basis states. This is what algorithms like quantum phase estimation exploit. It's not directly measurable, but relative phases matter. Qmod supports this with the phase statement. Conceptually, what phase expression scale factor does is apply a rotation to the angle or phase of each computational basis state in a superposition. The amount of rotation is proportional to the value the expression evaluates to for that specific state, scaled by the scale factor you provide, which is often related to pi.
So instead of changing the zeros and ones I might measure, it's tweaking something more subtle about the quantum state itself, the complex angle.
Precisely. Figure 6 shows this. After putting a variable x into a superposition, say representing numbers 0, 1, 2, 3, the statement phase, by 2 pi 4, applies a phase rotation to each state x. For the state 2, where x2, the rotation is 2 - 4 radians. For the state 3, where -3, the rotation is 3/104 sine by 4 radians, which is equivalent to 4 radians plus a full circle. This allows embedding the value of /2 into the phase.
That's really neat. And then there's arithmetic and amplitude. That sounds like where you encode data into the probability of measuring a state.
Correct. Amplitude encoding stores data in the amplitudes of the states, which can offer a significant logarithmic storage advantage over classical bit-string representations. Many advanced quantum algorithms, like those for linear system solving or quantum Monte Carlo, need to load classical data into amplitudes or output results in amplitude form.
But that sounds tricky to implement directly on hardware.
It is. The challenge is that encoding a general function into amplitudes is often a non-unitary process, which isn't directly executable on a quantum computer. It typically requires complex techniques like block encoding, where you embed the non-unitary operation within a larger unitary operation acting on more qubits, often involving an indicator qubit. Qmod tackles this with the assigned amplitude statement. The effect is what matters. Assigned amplitude expression, indicator qubit, encodes the value of the expression, evaluated for each state Qn, into the amplitude of the one state of the specified indicator qubit. This means the probability of measuring the indicator qubit as 1 is related to the square of the expression's value. Note that the expression's value must evaluate to something between -1 and 1 for this to work.
So the amplitude carries the information.
Exactly. Figure 7 uses assigned amplitude and a function tan_hamp to approximate the hyperbolic tangent function. It calculates tan x for each value of x in superposition and encodes that value into the amplitude of the in-qubit. This function effectively prepares a state where the probability distribution over the indicator qubit reflects the tan function applied to the input.
Okay, so Qmod provides native language features to handle calculations that result in digital bits, phase rotations, or amplitude encodings. That's quite a range. So what does all this actually mean for building quantum applications? How do these features come together?
It means algorithm designers can focus on the math and logic of their algorithm using familiar terms rather than immediately translating everything into sequences of low-level gates.
Less worrying about qubit allocation, uncomputation details, number representation.
It's exactly. Section 4 of the paper gives practical examples of this. Take piecewise linear approximation, figures 8 and 9. Approximating a function like tan using linear segments requires evaluating different linear equations, 8 plus bi, based on the range x falls into and combining the results. In Qmod, you write those linear equations using simple arithmetic expressions. Use the control statement, like a quantum if, and the within apply structure to select the correct segment and manage temporary qubits. The compiler takes this high-level description and figures out the complex gate synthesis to implement the entire approximation, managing precision and resource allocation automatically based on the target variable's inferred type.
So the complexity is hidden.
Largely, yes. Another strong example is in combinatorial optimization, using QAOA for the knapsack problem, section TBE. The paper looks at a specific instance. Maximize 3a plus 5b subject to 2a plus 3b equals 12, where a and b are quantum variables representing quantities. They show how you can use a Q-struct, knapsack force figure 10, to organize the problem variables naturally. For QAOA, you need to apply a phase proportional to the objective function. In Qmod, you implement this directly using the phase statement applied to the arithmetic expression representing the objective, negative 3 by a plus 5eb.
Negated because QAOA minimizes cost, right?
Correct. You minimize the negative of the objective to maximize the original. Now, the constraint 2a plus 3b equals 12 is crucial. How do you apply the objective phase only if the constraint is met?
Yeah.
Figure 11 shows an elegant solution. You evaluate the Boolean condition 2v upon a plus 3b plus 3 bytes equals 12, digitally using an ASSIGN statement, storing the true-false result in an auxiliary qubit. Then you use a control statement conditioned on that auxiliary qubit to apply the objective phase statement. And the within apply structure ensures the auxiliary qubit used for the constraint evaluation is automatically uncomputed afterwards. Clean resource management.
So instead of the developer figuring out the exact gate sequence for 3a plus 5b or the constraint 2a plus 3b equals 12 and how to link them with ancils and uncomputation, they just write the math expressions and the compiler handles the complex quantum circuit synthesis. That shift from low-level gates to high-level math seems like the core power here.
Exactly. It allows you to express the problem logic much more directly. And the paper mentions you can use that same expression syntax for classical evaluation, which is useful for post-processing results or setting up the problem classically.
And when you compare Qmod to related work, as discussed in Section V, you see where it stands out. Libraries like Qiskit or Pennylane give you powerful gate-level building blocks or tools for specific algorithm components.
Right, but you still have to compose them manually.
And handle many implementation details yourself. Qshag offers some nice features around allocation, but still requires explicit implementation decisions for operations.
Correct. The paper positions CRISP as perhaps the closest conceptually, also supporting quantum numbers and expressions. But it highlights that Qmod goes further with things like automatic numeric type inference, where Qmod figures out the optimal qubit representation for arithmetic results.
That automatic sizing thing.
And native high-level support for delegating the synthesis of phase and amplitude arithmetic to the compiler. That's a key differentiator. So, to wrap up, Qmod looks like a significant step forward in high-level quantum programming. It brings familiar programming concepts to the quantum domain and, crucially, offers native high-level support for arithmetic expressions that can be evaluated digitally or used to control phase or amplitude encoding.
Making it easier to write the code.
Much easier. By automating complex error-prone tasks like determining optimal number representations, efficiently uncomputing temporary qubits, and generating the necessary gate sequences for different arithmetic evaluation modes, Qmod directly addresses a major bottleneck in quantum software development. Allowing developers to express algorithmic logic, particularly arithmetic, directly in the language should boost productivity and could enable the development of more complex quantum applications that are currently just too difficult to implement at the gate level. The paper notes that future work will involve delving deeper into the specific synthesis algorithms the compiler uses and conducting quantitative evaluations to show how Qmod performs on larger use cases compared to other languages.
Showing the real-world impact.
Exactly, particularly highlighting the impact of features like adaptive storage and precision management. You can find more information on the Classiq platform, their documentation at docs.classiq.io, and their GitHub library.
Okay, so here's the final thought for you, our listener. Considering how Qmod abstracts away complex quantum operations like uncomputation and different encoding modes, letting you just write the math, how much more of the quantum weirdness can future languages abstract away? And what kinds of previously unimaginable algorithms might that level of abstraction ultimately unlock? Something to think about. That's all the time we have for this deep dive. Thanks for joining us as we explored Qmod and how high-level languages are aiming to speed up the development of quantum software. Join us next time when we'll be taking a deep dive into, well, you'll have to tune in to find out. Until then, keep digging into the knowledge.